So in this video, we're going to look at problems 5 and 6, or sorry, just problem 5 from your homework. And this is a challenging problem because it deals with computing a sum of two couples in 3 dimensions. So if you have a shoebox in front of you, if you have a shoebox somewhere in your house or just some small box, take it and put it on the surface in front of you. And the surface that it's sitting on is going to be the XZ plane, and the axis that's coming out of the top of it is going to be the Y plane. Now imagine trying to replicate this force couple pair that's being exerted at the base down here in the XZ plane. Hopefully you see if you take your shoebox, all that's going to do is rotate it about an axis that's coming out of the top. So this couple is going to purely induce rotation about the Y-axis. Versus this couple pair that we have here, it has a component kind of going into the box and out of the box, which is going to tend to, you can imagine if you took and you push this end of the box down and this end of the box up, it's going to rotate it about an axis coming out of this face or about the x-axis. It also has a component, if you project this onto the surface of the box, that is going to induce rotation about, sorry about that, thank God that was empty, about an axis that's perpendicular to the top of the box. So let's do the easy part first. Let's compute the couple associated with F2. Again, we note that it's the easiest way to do this is just going to be to draw this in the XZ plane, and that's exactly what I've done on this solution here. In the XZ plane, these two forces are separated by a perpendicular distance of 0.4 meters. What this notation means is that in the XZ plane here, the y-axis is coming out at you. So the big circle with a little circle in the middle means that the tip of that axis is coming directly towards you. So hopefully you notice that if you look at the rotation that these two, that this force couple pair would induce, it's going to be in the clockwise direction about the positive y-axis. Remember that clockwise rotation about a positive axis, we actually denote as negative. So that's how I'm getting this negative here. But the magnitude of the force is the magnitude of the couple rather, it's pretty easy to compute. You just take the magnitude of the force, multiply by this perpendicular distance, and you get minus 7.2 Newton meters in the j-hat direction, which means that it is clockwise rotation about the positive y-axis, which if you have the shoebox in front of you, if you don't knock down your coffee mug, you'll convince yourself as well. So what about the actual F1 force? How should we handle that? Well, the key point is you want to decompose it into components in the XZ plane and components in the YZ plane, or kind of components going up and down that are going to rotate it about X, and components that are on the surface or top of the shoebox that are, again, just going to rotate it about Y. To get the components that are on the top of the shoebox, notice that those forces are adjacent to this 40-degree angle. So you're going to want to take the cosine. So that's this first step of F1 times cosine 40. I'm just projecting those vectors down into the XZ plane. And notice in the XZ plane, if you think about the one that's closest to you, it's kind of going out towards positive X, and the one that's farthest away is going towards negative X. And they're separated by 0.75 meters. So that's why when I draw this picture in the XY plane, perpendicular distance is 0.75. The one that's most towards us is going out to the right. The one that's farthest back is going back to the left. If you think about the nature of that rotation, it's going to be counterclockwise rotation. Counterclockwise, again, about the positive y-axis. So since it's counterclockwise about the positive y-axis, we'll denote that rotation as positive j. So when we add all these vectors together eventually, this vector and this vector, they're going to destructively interfere because this is inducing counterclockwise rotation about y versus the top pair is inducing clockwise rotation. In order to finish this problem off, though, you need to decompose this vector into the actual the components in the YZ plane. So those are opposite of that 40-degree angle. That's why for getting that magnitude, we're going to use the sine function. So 23 times sine basically gives me the components of those couples that are going into and out of this top of that shoebox. And they're going to induce, again, they are in the YZ plane. If you notice, the one that is closest to the actual y-axis is going up, and the one that's further away is going down. So that's why these are drawn in this way, with that being y and that being z. You got up and you got down. 0.75 perpendicular distance. If you take that and multiply by the projection of the vector into the YZ plane, you will get a magnitude of a rotation. And the key point to notice is if you're going up and down, that is counterclockwise rotation about the positive x. Remember that the unit vector for the x-axis is I hat. So this is going to be something positive times I hat. How do you finish the problem up? Well, you know that those are the 3 moments that describe the rotation associated with the first couple and then the projection of the second couple into the 2 dimensions. So once you add them all up, the key point is it's just a vector, and it's got an x and a y component. So you can find its magnitude by Pythagorean's theorem, square root of the sum of the squares. In addition, if you actually draw it in the xy plane, and remember what this direction is showing you is what axis this thing looks like it's rotating about. So the key point is there are no pairs of actual forces here. If you think about the rotation, there's no rotation about the actual z-axis in this case. And if you think about how well, I don't want to make this video too long or go into too much detail, but hopefully you can see that there's no rotation about the z-axis. So the effective axis of rotation is going to be in the xy plane. You can actually determine its direction by using standard trigonometry. You know the x component, you know the y component. So find theta x by simply taking the inverse tangent of my over mx. Find theta y by noting that 90 theta y plus theta x has to equal to 90 degrees. By definition, I'm labeling theta y here with this convention. And by definition, if it's in the xy plane, right, the angle to the z-axis is going to be 90 degrees. So I know that's a really confusing one. If you rewatch this video a couple times, it might help a little bit. But the thing that will help the most is to actually set a shoebox on a table in front of you and kind of try to recreate the actual situation.